So as we just discussed, there's a number of reasons to prefer spaced mixed trials or slow event-related designs. There's also some good reasons to prefer a blocked design. However, there clearly is one large difference. As I mentioned earlier, blocked designs tend to be much more powerful, and the reason is that in the same amount of time, you can just pack many more trials in a block design compared to a slow event-related design. If you look at this graphic, I think each of these is just about 12 trials. It means that in the same amount of time, I managed to pack 24 trials of type A, maybe looking at faces, 12 and 12, and another 12 of type B, maybe looking at houses. In this exact same amount of time, however, I think I've only managed to squeeze 16 trials, which means just about 8 faces and 8 houses. So that's why earlier I said that block designs are just much more statistically powerful, because you're sampling much more the brain while it's carrying out the cognitive process of interest, which is looking and processing the pictures. And the reason for it is that during slow event-related designs, we need to set each trial apart from 10 to 12 seconds. And so if you need to wait 10 to 12 seconds in between each trial, time adds up very quickly. After 10 trials, you have, for any 10 trials of sampled cognitive processes, you have 2 minutes of just having to wait for the hemodynamic response to go back to baseline. And that's why people slowly started converging towards rapid mixed trials, also known as fast event-related designs. And the difference between the spaced or the slow event-related design and the rapid mixed trial or the fast event-related design is that you simply don't wait in the rapid one, you simply don't wait for the hemodynamic response to come back to baseline before you hit it with a new trial. And as you can tell from this graphic, you can now put in many more trials. In other words, we just have to wait a few seconds in between our trials, as opposed to having to wait 10 to 12 seconds. And so now, in the same amount of time, as you can see here, you can just pack way more trials of both conditions compared to the slow event-related design. So this is very positive, because you, in the same time, without having to extend your experimental design, you can put in many more trials, and this helps you regain some amount of power. However, the big problem is that now the hemodynamic response, let's say for the first trial, overlaps with the hemodynamic response of the second trial. And the one to the second trial overlaps with the response to the third trial. And we need to find a way to disentangle how much of the bold response comes from one trial and how much comes from a different trial. Let me show you what I mean. So let's just say this is a toy experiment that I created. Let's just say that our experimental design has a little rest, then a trial, then another rest, then 2 trials back to back, then rest, then 1, 2, 3, 4, 5 trials all nearby each other, then a little rest, then 2 trials, then rest, and another trial. If you were to look at the bold response to this, remember, the bold response is not on-off immediately. It takes time to build, maybe 6 seconds, and then needs another 6 to 8 seconds to come down. So if you have trials nearby, the bold response won't have time to come back down. We'll just go back up again. If you look at this graphic, that's exactly what you see. So the response to trial number 1 is the regular bold response right here. But then see, you have 2 trials back to back. So effectively, you just get a double response. And then you have 5 trials back to back, and see it goes up for the first 2 trials. It peaks, it comes down, and as it comes down, you hit the participant again with a new trial. And so it goes back up again, and there's another trial, the 4th right there. Then there's a little break, so the bold response comes down. And then as it's coming down, you hit them again with another one, and boom, the bold response goes up again, et cetera, et cetera. And see, the problem is, look at the big one in the middle. How can you tell which part of this big curve is due to trial 1 sorry, the first of these 5 trials. How much of this curve we can ascribe to the second trial? How much of this curve we can ascribe to the third, the fourth, and the fifth? Right? It's difficult to look at this big, triple mountain and say, well, okay, so this much of it must come from trial 1, then this much of it comes from trial 2, et cetera, et cetera. So we need a way. We need a way to tease these two apart. The beauty of it is that if we can assume or close to enough that the hemodynamic response is a linear system, then we can actually disentangle how much of this big mountain comes from trial A and how much comes from, let's say, the first trial, how much comes from the second, how much comes from the third, the fourth, and the fifth. Okay. So if we can assume that the bold response is linear enough, then we can disentangle these trials and we can recover and we can sort of compute how much of that big sort of triple mountain is due to each one of the individual trials. Now, what does it take for a system to be linear? Well, 2 things mainly, scaling and superposition. So let's look at each one in turn. So scaling is simply the idea that the bold response scales linearly with the intensity of the stimulation. So if we have a small stimulation, which is represented by this little red to orange gradient, then the bold response is this much. And this is a cartoon example. If we had a stronger stimulation, then the bold response would be stronger. And if we had an even stronger response, the bold response would again linearly scale up. Okay, so this is scaling. Now, the question, of course, is this true of the bold signal? Well, some people have looked into it. Here's one example, and I know it's a bit of a crowded graph, so let me orient you to it. So on the x-axis, as usual, we have time. On the y-axis, we have the percent change of the signal compared to a baseline. So you start with just looking at a blank screen, and then you compute once you start the stimulation, which starts at the 0 point, by how much does the signal go up? So, Savoy and O'Craven did this experiment under 3 different conditions. In condition 1, you were shown a pulsed visual stimulus for 34 milliseconds. And the response you got was this. Then in condition number 2, you were shown the same stimulus, but for 100 milliseconds. And you see this response. Condition number 3, you were shown the same stimulus, but for 1 second, and you get this big response. And so the question now is, well, does the response scale linearly? If that were the case, then 100 milliseconds would have to be exactly 3 times the response to 34 milliseconds, right? If it scales linearly, it means that the response to seeing 100 milliseconds of visual stimulation should be exactly 3 times the response to 34 milliseconds. But if you look at them, they scale, but they don't seem to scale very linearly. Similarly, the response to 100 milliseconds of visual stimulation should be exactly 1/10 of the response to 1000 milliseconds, or 1 second. So if I took this and multiplied it by 10, I should get exactly the response to 1 second. It doesn't seem to be exactly the case. So does it scale? Yes. Stronger stimulation, in this case, longer stimulation, does induce a greater response. Does it scale linearly? Not exactly. Now here's a wonderful and more thorough example of the same idea by Robson and colleagues. They used a very ingenious approach. What they did is they played a number of auditory tones to the participants and then looked at the bold response. But they set up the design in this very clever way so that they could they could try to predict the response to more tones from response to fewer tones and look at linearity. Let me show you what I mean. So what you're seeing here in this line right here is the bold response after one tone. And their idea was, well, if the system is linear, I should be able to take this response, multiply it by 2, and approximate the response to 2 tones. And so that's what they did. And then they actually played the 2 tones, and they looked at what the response was and how close was the predicted to the actual. And I know here it's hard to tell, but there's one bold line, which is the actual response to 2 tones. And there's a lighter line just above it that is the inferred response to 2 tones. So if you take the response to 1 and multiply it by 2, you get the line that is a little bit above. If you actually look at what you get for 2, it's the bold line. Now we can keep playing this game. If you take the response to 1 and multiply it by 4, you ought to approximate the bold response that you actually see if somebody listens to 4 tones, which is here. And again, in bold, you're seeing the actual response to 4 tones. In the lighter color, in the lighter line, you're seeing the predicted response. So if you take this response and multiply it by 4, and you can notice that they're starting to diverge. And we can keep playing this game. If you take the response to 1 multiplied by 8, we should be able to approximate the actual bold response for when somebody listens to 8 stimuli. And we can do that with 16, 32, 64, 128. And as you can tell, there's an obvious trend. Our prediction keeps growing linearly, right? The faint line. But the bold response does grow, but not as expected, not linearly as expected. It keeps extending, but it doesn't keep growing. So just taking the response to 1 and multiplying it, say, 16 times, doesn't really approximate the response that you actually get for 16 tones. So does the system scale? Yeah, it sure does. It just doesn't seem to scale linearly. And then, of course, you can continue playing this game. So you can take the actual response to 2 tones, multiply it by 2, and see if it matches the actual response to 4 tones. Multiply it by 4, and see if it matches the actual response to 8 tones, which is the one you see again in bold. And the prediction is the one that you see in the lighter color. And then you can take the response to 2 and multiply it by 8 times and see if it matches the response to 16 stimuli, which is here. And you can see the trend still is that, yes, the system scales, but our prediction keeps failing. Our prediction keeps overestimating just how much response we get from the actual stimulation. And we could get the response from 4, right here, multiplied by 2, see if it approximates the response to 8, multiply it by 4 and see if it approximates the response to 14, and so on and so forth. And you will notice that the trend remains the same. However, you will also notice that if instead of taking the response to 1, for example, we take the response to 4, our error becomes less and less, right? The difference between the predicted and the actual becomes less and less. In fact, by the time you take the prediction to the actual response to 64, if you multiply that by 2, you get something very similar to the response to 128. So what does this mean in terms of the response? Well, it means that it is linear in one part of the envelope, and it's not quite as linear in the other part of the envelope. If you take response to brief stimulations, then you cannot multiply them to correctly approximate the response to long stimulations. But by the time you're at something, at 4 stimulations, you actually can approximate pretty well higher stimulation. So this means that in the early part of the curve, the response is not linear. In the late part of the curve, the response is linear. And in fact, if you go back to the slides on the relationship between neural activity and bold response, in fact, and vascular response, you should be able to find out exactly why it is that the small trials don't approximate well long trials, but medium trials do approximate pretty well long trials.